Right, in this video, we're going to talk about suggested homework problems from 5.6, where we'll discuss L'Hopital's rule and a little bit about indeterminate forms. So there are some good indeterminate forms that we like, specifically 0 over 0 and infinity over infinity. And there are some other indeterminate forms that we really don't like. We have to manipulate them a little bit to get them into the form of 0 over 0 or infinity over infinity before we can really do anything with them. More on those when they show up. So let's go ahead and start with number 7. And it asks us to evaluate this limit 2 different ways. First with our old techniques, and then with the new technique for L'Hopital's rule. So limit as x goes to 4, 3 times x minus 4 over x plus 4 times x minus 4. And those will cancel. This is limit as x goes to 4 of 3 over x plus 4. It's 3 over 4 plus 4 is 3 over 8 for my limit. Now to use L'Hopital's rule, limit as x goes to 4, 3 times x minus 4 over x squared minus 16 is going to go towards 0 over 0, which is one of our good indeterminate forms. So L'Hopital's rule can be used. L'Hopital's rule tells us to leave the limit here and take the derivative of the numerator and the derivative of the denominator, and then evaluate this new limit, and it should have the same value as the original limit. Only works when I have 0 over 0 or infinity over infinity for my direct substitution. So make sure that you show that to show that you're allowed to use L'Hopital's rule. Let's go ahead and look at number 11. Limit as x goes to 0, 2 minus cosine of x, 2 minus 2 cosine of x over 6x, and we'll pull out the 2 over 6 here. Limit as x goes to 0 of 1 minus cosine of x over x. It's 1/3 times, that's one of our special trig limits, which is 0. So 1/3 times 0 is 0. Now let's look at the limit as x goes to 0 of 2 minus 2 cosine of x over 6x. This is 2 minus 2 over 0 is 0 over 0, which is an indeterminate form. That's good, and I get to use L'Hopital's rule. So limit as x goes to 0 of 0 plus 2 sine x over 6 is 2 times 0 over 6 is 0 over 6 is 0. And that's the same answer for both parts. Let's go ahead and look at number 17 now. And these problems tell us to use L'Hopital's rule if necessary. So I believe that that implies that we should try to use other techniques first before using L'Hopital's rule. So 25 minus x squared plus 5 over root 25 minus x squared plus 5 is limit as x goes to 0 of 25 minus x squared minus 25 over x times root 25 minus x squared plus 5. 25 minus 25 is 0. And I have limit as x goes to 0 of negative x squared, x times root 25 minus x squared plus 5. X goes into x squared x times, limit as x goes to 0 of negative x over root 25 minus x squared plus 5 will give me 0 over 5 plus 5 is 10 is 0. And that's my answer. Let's look now at number 21. Definitely doesn't need to have L'Hopital's rule. If I try direct substitution, this is going to 0 over 0. I know that that means in this case that there's a common factor of x minus 1 over x minus 1. I also have limit as x goes to 1. This is x plus 1 times x squared plus 1 in the denominator. My remaining factor in the numerator, I'll show you by synthetic division, is going to be x to the 10th plus x to the 9th plus x to the 8th plus x to the 7th plus x to the 6th plus x to the 5th plus x to the 4th plus x to the 3rd plus x to the 2nd plus x plus 1. So how did I get that? To use synthetic division with 1, and this is 1x to the 11th, 0x to the 10th, 0x to the 9th, 8th, 7th, 6th, 5, 4, 3, 2, 1, and 0 is -1 there. So bring down the 1. These are all going to be 1. And then that's going to be 0. That's how I got 1s for all of these coefficients. These will cancel. That limit is going to give me 1 plus 1 plus 1 plus 1. There's 10 of these parts with x, and then another 1. So that's going to give me 11 over 2 times 2 is 4 is my limit. Now let's use L'Hopital's rule and show you how much easier that would have been. Limit as x goes to 1 of 11x to the 10th over 4x to the 4th is 4x to the 3rd, excuse me, 4x to the 3rd. This is x to the 7th, so limit as x goes to 1 of 11x to the 7th over 4 is 11 over 4. It's the same answer. L'Hopital's rule is much better there to avoid that long division of polynomials or synthetic division or whatever. Let's look at 23. 23 is not that bad to do the old way. So that's limit as x goes to 0 of sine of 3x times limit as x goes to 0 of denominator of sine of 5x times limit as x goes to 0 of some stuff that I'll need here. So I need a 3x in the denominator, a 3x in the numerator to balance it out, 5x in the numerator, a 5x in the denominator to balance it out. These x's can cancel. That leaves me with 3/5 times 1 is 3/5 for my limit. 31. Got a couple different ways that I can think about 31. So limit as x goes to infinity, x over root x squared plus 1. I'm going to think about it this way. And as x is going to positive infinity, that this square root of x squared is going to be x, which is the same sign as this positive x right here. This is really an absolute value of x. An absolute value of x is x when x is greater than 0. I'll say or equal to 0 here, negative x when x is less than 0. I'm definitely on the greater than 0 side, so limit this goes to infinity. Let's just write it out all the way. And limit as x goes to infinity, 1 over root 1 plus 1 over x squared, 1 over root 1 plus 0, 1 over root 1 is 1 over 1 is 1 for my limit. Let's look at 35 now. 35 is the first one that I really do have to use L'Hopital's rule. So limit as x goes to infinity, ln of x over x squared. This will go to infinity over infinity. And so I'm going to use L'Hopital's rule. Which tells me to leave the limit out here alone, take the derivative of the numerator and the derivative of the denominator. And I'm going to rewrite now. And then that's going to go to 0. And that's my answer. All right, I'm going to modify the instructions for these last couple problems because I really have no way, even with the graphing calculator, to show you what the result is. For part B, I'm just going to do parts A and B here. So limit as x goes to infinity of x ln of x. If I try direct substitution, that's infinity times infinity is infinity. And so that is not an indeterminate form. I know exactly what that limit is. The limit does not exist. Because it increases with that bound. Or I could say that the limit as x goes to infinity of x ln of x approaches infinity. And that's the short way to say what I just said with all those words. But it's more proper to say that the limit does not exist because it increases with that bound. This is one that I actually can show you that it goes off to infinity. This is really the only one that graphing would really show you anything. So there it is going off to infinity right there. Let's look at 47. Limit as x goes to 0 from the right of e to the x plus x 2 over x. So as I plug in 0 from the right here, this is going to be approaching 1 plus 0, 2 over 0 from the right is going to approach 1 to the infinity, which is an indeterminate form. It's not the indeterminate form that the kind of indeterminate form that lets me use L'Hopital's rule right away, but it is an indeterminate form. So we have an indeterminate form of 1 to the infinity. So we'll have to use some stuff here to be able to tell you what that limit is. I'll call that limit L. Limit as x goes to 0 right of e to the x plus x to the 2 over x. And I'll take the ln of both sides. Limit as x goes to 0 from the right, ln of e to the x plus x to the 2 over x. Ln of L is going to be limit as x goes to 0 from the right, 2 over x times ln of e to the x plus x with my log properties. If I try direct substitution now, the way that this is written, this is going to go to infinity times 0. That's not quite what I want. I need to fix that to be 0 over 0 or infinity over infinity. So ln of L is limit as x goes to 0 from the right of 2 ln e to the x plus x over x. Now if I try direct substitution, that's 0 over 0, which is a good form to use L'Hopital's rule with. Leave the left-hand side alone because it's not the limit, or it doesn't have a limit that I'm using L'Hopital's rule with. It's this limit on the right that I'm using L'Hopital's rule on. So leave the limit alone. 2 over e to the x plus x times the derivative of e to the x plus x is e to the x plus 1 over 1. So ln of L is going to be 2 over 1 plus 0 times 1 plus 1 over 1. ln of L is going to be 2 times 2 over 1 is 4 over 1 is 4. So L is equal to e to the fourth. So if I go back to the original, what was L? It was limit as x goes to 0 from the right of e to the x plus x to the 2 over x is equal to e to the fourth. Okay, can't prove that to you with the calculator, but that's the correct answer. Let's look now at number 51. Limit x goes to 0 from the right of 1 plus x to the 1 over x. This is one of the ways to define e. I'm going to prove that to you, but this is one of the ways here. So for direct substitution, this is going to go towards 1 to the infinity, which is an indeterminate form. So for part A, we're having an indeterminate form of 1 to the infinity. Part B, L is equal to this limit. So ln of L is equal to limit as x goes to 0 from the right of ln of 1 plus x to the 1 over x. ln of L is limit as x goes to 0 from the right, 1 over x times ln of 1 plus x. If I try direct substitution now, this is infinity times 0, not quite right. I need to take another step to get it to be infinity over infinity, or 0 over 0. Now if I try that again, this is going to give me ln of 1 is 0 over 0. That's correct. I'm able to use L'Hopital's rule now. So ln of L is equal to limit as x goes to 0 from the right, 1 over 1 plus x over 1. So that gives me ln of L is equal to 1 over 1 over 1 is 1 over 1 is 1. So L is equal to e to the first is e. So limit as x goes to 0 from the right of 1 plus x to the 1 over x is equal to e. So another definition for e, just so that you know it, is probably one that you know, like that, and it's basically the same thing. This part's going to 0, small positive number. This is a big positive number here. This is a big positive number here. It's exactly the same thing. So both of these are definitions of E. All right. Let's look now at 75. Y is equal to x to the 1 over x. We're given the restriction that x has to be greater than 0. Some funky stuff happens over on the left-hand side of x to the 1 over x if I start using negative values, so we're just not going to do that. Let's look at what this would look like. X to the 1 over x, zoom 6. And so this is going to increase, reach a maximum, and then decrease towards a horizontal asymptote, which is what I want to show you is happening with the calculus here. So I'm interested in the limit as x goes to infinity of x to the 1 over x. That would be approaching infinity to the 0, which is an indeterminate form. And so I'm going to have to take ln of L is equal to limit as x goes to infinity of ln of x to the 1 over x. So this is ln of L is equal to limit as x goes to infinity, 1 over x times ln of x. And so this is approaching 0 times infinity, which is not quite right. Ln of L is limit as x goes to infinity of ln of x over x, which is going to infinity over infinity now. That's good. And I can use L'Hopital's rule. So ln of capital L is equal to limit as x goes to infinity, 1 over x over 1 is equal to 0 over 1 is 0. So L is equal to e to the 0 is 1. So limit as x goes to infinity of x to the 1 over x is equal to 1. And I can show you that that is true here. Let me just graph that horizontal line for you and show you that we're getting closer to 1 from the top, but we're not ever getting there no matter how far out to the right I go. It has a horizontal asymptote of y equals 1 only on the right hand side, not on the left hand side. Now let's try and find its maximum value, which is right over here somewhere. And I'm going to do that by, again, going back to y equals x to the 1 over x. And I want to differentiate implicitly, since this is a function of x, to another function of x. We talked about that here, and I'm going to use logarithmic differentiation to do that. This was discussed in a previous section. So 1 over x times ln of x is going to give me ln of y is equal to ln of x over x. Now, when I differentiate 1 over y times dy dx is equal to derivative of the top times bottom minus derivative of the bottom times the top all over the bottom squared. So dy dx is equal to y times, this is 1 minus ln of x over x squared. And that is going to make this dy dx is equal to x to the 1 over x times 1 minus ln of x over x squared. Bring these together, dy dx is x to the 1 over x minus 2, so 1 minus ln of x. So it's undefined. X to the 1 over x is undefined when x is 0. I'm just going to tell you that there's a little bit of a hole right there. Let me show you that if I try and trace 0 here for blue function, there's no value of y there. So that's another reason why we are saying the x has to be greater than 0, going up, and then I start to come back down towards y equals 1 here. So let's look at what 1 minus ln of x equals 0 does. Then ln of x is equal to 1. X is equal to e to the first. To use my first derivative test, I could try to use my second derivative test here for extrema. Now that I have this critical number, I could find the second derivative and plug it in. But that's just too nasty to try and find the second derivative of this. So I'm just going to use my first derivative test here and say that I'm starting at 0. And then I have a critical number here of e to the first. And then when I am looking at this form right here, something between 0 and e, like 1 minus ln of 1. So 1 minus 0 is a positive 1 over 1 squared. So that's all 1. And 1 to the 1 over 1 is 1 to the first is 1. So 1 times 1 is a positive 1. So I'm increasing here on this interval. And I see that I'm increasing for a little bit before I start decreasing. But I'm going to pick something that is bigger than e, hopefully something that comes out with a nice number here for ln of x. So I'm going to pick e squared. And so that's going to be 1 minus 2. That's a negative 1. This will be a positive number. This will be a positive number. Positive times a negative over positive is a positive times a negative is a negative. And this is decreasing. So I have a local max at x is equal to e. And then y of e is equal to e to the 1 over e. So my local max is at the point e to the 1 over e. All right. We have some error analysis problems now to kind of wrap things up. So when you see these types of problems in the book that have the X next to them, it means that there's a mistake in the problem and they want you to find the mistake. So in 79, it looks like the student used L'Hopital's rule without establishing that they could use L'Hopital's rule. So let's check that out. Let's see if we can use L'Hopital's rule by trying direct substitution first. So this would approach 3 times 4 is 12 plus 8 plus 1 over 4 minus 2 would approach 21 over 0. Well, that limit does not exist. And L'Hopital's rule does not apply. Because we did not obtain zero over 0 or plus or minus infinity over plus or minus infinity via direct substitution. So we could not use L'Hopital's rule here. So that's the problem, is that L'Hopital's rule was used and it couldn't be used. And it's an easy mistake to make when you forget to check with direct substitution to make sure that you get 0 over 0 or infinity over infinity before you try to use L'Hopital's rule. Don't just jump into it because you see a rational function. All right, 81 is going to probably have a similar error in it. Limit as x goes to infinity of e to the negative x over 1 plus e to the negative x. So when I try direct substitution, it's going to be 0 over 1 plus 0. 0 over 1 is 0, so that limit does exist. And I don't need to use L'Hopital's rule. I can just find it directly. So L'Hopital's rule does not apply here either. Right? The limit can be evaluated directly. And that's it for this video. And we'll come back next time and talk about section 5.8. We'll talk about intervals that give us arcsine, arctangent, or arcsecant functions for our antiderivative. So inverse trigonometric integrals is the topic there. So see you for the next video.